Assalamualaikum.
Waalaikumsalam.
Pak.
Oke ya, oke
Okey,
ya,
okey.
clear ya, sudah clear. Gambar pun clear ya.
Gambar nampak.
Oke, oke lah. Gambar pelajar tak payah ini ya, tak payah on ya.
Gambar pelajar.
Apa
Tak payah.
video. Pelajar tak payah saya pun tak
Betul.
payah lah. Tak payah.
Ah,
Uh,
Pak Pina.
Oke lah, saya rasa
Tunggu
kita
dah ke
tunggu. Kita tunggu 5 menit ya. Mungkin ada pelajar agak sukar dia join. Bagilah
Kita
masa
tunggu orang
sedikit.
join.
Mungkin ada beberapa pelajar yang memang tak ada wifi, tak ada internet. Saya rasa boleh dimaafkan lah dokter ya.
Assalamualaikum Prof.
Waalaikumsalam.
Maaf Prof, ini kameranya
Tak payah.
Iya, Prof.
Video tak payah buka.
Ini pakai
Ya, video tutup. Voice dia.
ya.
Oke, setakat ini ada 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 7 ya. 7 pelajar. 7 pelajar join dengan Dr. Onira dan saya sebagai ini ya, pemberi kuliah.
Pak.
Yap.
Boleh share screen?
Ya, oke. Saya try. Yap. Oh, sorry. Recording siapa start? Dr. Onira ya?
Ya, saya record.
Oke. So, Oke lah, kita start ya. Oke, Assalamualaikum. Good morning, everybody. Today we will talk about MEMS and NEMS, a subject of MEMS design. Yeah. So this topic will include device design, process design, theoretical and simulation aspect in the MEMS design, and also case study. So this is a lecture week 3. Actually, for this week 3, we have 4 subjects. First and second subject will be about MEMS design and MEMS fabrication. Okay, my name is Associate Professor Dr. Jumril Yunas. Okay, this is our overview for this subject for MEMS design. First, we will talk about MEMS overview, a brief overview about MEMS, and then we will talk about device and process model. Then I'll show you theoretical aspect or theoretical analysis aspect in MEMS design, and we will close our lecture with a case study. This is introduction. MEMS is an abbreviation of micro-electromechanical systems. MEMS use the principle of mechanical, electronics, or physical phenomenon to function, while NEMS is actually more theoretical, as there are only few working devices currently. So MEMS has the scale between 1 micron up to 1 mm. So if we consider human has a size about 1 meter or above, so we can see that water drop has smaller dimension, about 1 mm, and then if we go down to the virus or cell dimension about 1 micron, then MEMS is between a water drop and virus size. Yeah, so it's a small size. Then NEMS has the size scale of between 1 nanometer up to only 1 micron. It's much smaller than MEMS. So NEMS has a size of about a DNA size. Okay, yeah. MEMS device are entity that is function using electromechanical principle. MEMS have found its important role for widespread application. Regarding to its functionality, MEMS and NEMS can be classified into 3 broad categories, such as sensors, actuators, and also any passive 3D structures. Yeah, can be considered as a MEMS device. Sensors is a device that convert mechanical, thermal, or other forms of energy into electrical energy, whereas actuators do the exact opposite. So it converts the electrical power into a mechanical movement. So some application of MEMS device have been actually available in the market. They are RF MEMS for MEMS resonator and RF filters and also switch. There are also microtransformers and inductors or variable capacitors and also MEMS-based reconfigurable antenna. For energy harvester, MEMS are available as piezo MEMS microgenerator, electromagnetic generator, and also MEMS supercapacitors. MEMS sensor and actuators can be found as accelerometer, pressure sensor, fingerprint sensor, optical sensor, magnetometer, gyroscope, switch, and also optical stabilizer. So we can find many MEMS sensor and actuator already used for many type of instrumentation. So we can find also MEMS for microspeaker and microphone. And in field of biomedical, we can find MEMS biosensor and detectors as biocell manipulators for blood filtration, virus detector, and separator. And the most current application of MEMS are also already available in the market as in the microfluidic devices such as microheater, microchamber, microchannel, microneedles, microvalve, and micropumps. Okay, this is an example of MEMS device as actuators. So this device consists of movable membrane, permanent magnet, and also electromagnetic coils. This concept can be found in microspeakers or microfluidic pump and many other biomedical instrumentation. So theoretically, for the function of the actuator, when electrical AC current flow through the microcoil, so magnetic field will be generated and interact with the magnet inside the membrane. Yeah, and then this interaction will produce magnetic force. Yeah, that push and pull the membrane. So this magnetic force can be calculated as the height of magnetic inductance of the permanent magnet, the area of the magnet, and also the magnetic field gradient between the membrane and the coil. So this interaction will create deformation of the membrane that can be calculated as the function of the magnetic force and the mechanical flexurability D. Okay, that was a brief overview about MEMS. Now we talk about the design of the MEMS device that can be that can be separated in two aspects. First is about the device or the system design, and the second aspect about the process design. So this is the scope of our lecture today. For the device or system design, this aspect include the design of the structure, the geometry, the choice of the materials, and also the design of the layout, and also design how to integrate every part of the MEMS structure. The methodology to do the design, so we can use the theoretical calculation, simulation or model, and also we can design how the experiment should be done. Yeah. So this methodology should consider the properties of the mechanical properties of the material or the structure, the electrical properties, optical properties, or the microfluidics aspect of the system. And then for the process design, we consider the chemistry process and also physics process. So that means in this area we have to know about the chemistry or the physical aspect of the device. So for the methodology, we have to to do first the process simulation, and then we can go to experimental process. For the process fabrication, we should consider also the facility, how to fabricate the device. That means we need clean room class 100,000 and also 10,000. Yeah, and some also use a standard process lab, such as chemical lab. So this is the first step. Yeah, we should design the device, and then we come to the next step, process design. When we finish the design activity, then we can go to the clean room or to the lab to synthesis or to create the structure, and then we characterize and optimize. Finally, we do the testing of the fabricated device. So in MEMS process, so we can call that it should be a high investment. So the clean room is cost very expensive, but the device that we have fabricated as low volume. So we can call that this technology is a low volume technology, but high volume product. Okay. So this slide show the MEMS design methodology. Actually, there are currently no single standard MEMS process. So it is different with IC process, which have a single standard MEMS process. Yeah. So for MEMS, each device has its own process. Tools for the design and model of MEMS device. We can use some tool to design the device. We can use some tools to design the process, how to create the structure, how to fabricate a system. And then we can also use some analysis tools. For the device design, we know some tools such as Cadence, L-Edit, Spice, MATLAB. If we use a theoretical calculation, this could be a good tools. And then we can use CorelDRAW, AutoCAD to design the layout. Another tools for the process design such as Supreme, IntelliSuite, anisotropic etching. This is the tool special for analysis of bulk silicon etching. Yeah, we can also use CoventorWare and ANSYS. Some other tools can be used also for analysis. For finite element analysis, so you can use CoventorWare and COMSOL. So these two softwares are the common software we use in our lab. This is some figure to show how the layout of some simulation tools. This is for Supreme, so we can here design the structure, how we put the oxide layer, metal layer, polysilicon layer, and also substrate. etc. So this is the layout result from CovenTware. So we can create the structure meshing, and then we can simulate the functionality of the device. This also another tools to simulate a process, or to model a process fabrication, such as etching process. Using this using CAD tools that can accurately predict the physical etching and process of 3D MEM structure. This is the layout we create during our simulation, and this should be the result. Yeah, this is the real etching result. Yeah, after etching, that is captured using SEM. In MEMS process, the creation of the structure follow the batch process. So batch process is the standard process in CMOS process. Yeah, that means it needs the precision between the layers. Batch process mean also stacking and structure formation is done layer by layer. This fabrication process have limits about how close part of a circuit can be together, how minimum the size of the conductor line, the transistor, etc. So this is driven by the precision of the equipment, the precision of the alignment between the step, because we are doing with several layer which should be connected each other. Therefore, the design rules should be defined that tell the designer what is allowed by the process, such as we have to consider the contamination, the selective removal, selective masking, etc. However, significant trade-off involved in creating the design rule for a process, such as for conservative rules should give high yield. Aggressive rules can improve the performance and the density. Yeah. However, it is not high precision. So why we need design rules? We need the design rules to keep the dimension as a design. We don't want the result is different with what we design using the CAD. Yeah, this is also to be able to tolerate some level of fabrication errors, such as misalignment or contamination, such as dust. If we know that the structure of MEM is very small, between below 1 mm. So if particle of dust, so okay, on a device surface, so it could break the device function, can be broken. And also the process parameter also can be considered. So this is the design rules. The rules defined in general in terms of the width of the via, the width of conductor line, the separation between the metal line and also overlap. So we can see here the dark area as a line over the layer. So that means we can consider the precision of the alignment of the layer. The design rules are not a guarantee of device functionality. However, following the design rules, we can maximize the chance that the chips will work and yield when you fabricate many copy of a chip. This is the actually this is the design rules that commonly used in IC fabrication. Okay, this slide show some experimental case. Yeah, why we need the design rules. We can see here some error can happen during fabrication, such as misalignment. So that means we have to consider the space between the via and the conductor line. Yeah? And then also it could happen increasingly of a via size. Yeah, for etching process sometimes happen over etch. Yeah, which can damage also the connection between the line. This is some cases that I have taken from microcoil fabrication. Okay, we come to the third section about theoretical analysis and simulation. This slide is aimed to give overview about the working mechanism of the system. To understand the role of physical structure and technical data such as geometry, material, etc. To improve the quality, to ensure the functionality of the system. So therefore, the simulation is that to imitate the operation of a real-world process or system. The role of simulation in the research is to use the tool to understand the general system principle, and to generate insight. If you want to understand how is the mechanism of some MEMS function, and also to evaluate the performance. Sometimes we fabricate the device and then we know how good is the product, so we can revert to our simulation analysis. And the simulation also can be used to compare, to validate of an approximation. Simulation actually are the only general method for solving many body problem. Other method, we can use some approximation, or we ask expert about the mechanism of some device. And then experiment is limited and expensive. Therefore, we can do simulation to see the to study the material or the device. Simulation can complement the experiment or some work in our master or PhD study, they use only simulation. If they want to see the validity of the simulation, they send the concept to the outside to be fabricated. But here in IMEN, we have complete facility, so we don't need to send out the sample. So we can try to do some experiment here in IMEN. Yeah. Simulation are easy, even for complex system, and they can scale up with the computer power. So complicated structure need more power computer memory. Some challenge of using simulation work. Sometimes we have lack on the basic knowledge. So therefore, our simulation analysis it is far from the real from the theory. Yeah, far from the theory. If we use theoretical calculation, therefore we have to consider what approximation should come in. And another challenge is the computer memory, and the solving time is limited. If we use a few layers for short period of time, then the system with many structure and very small scale are more problematical. So we need more power computer, more memory, and long simulation time. We have to estimate error. Yeah, so such as we have to consider the statistical and systematic, and also we have to manage even more complex boundary. Many of parameter of MEMS device depend on geometry and structure. Therefore, it is important that the layout and analysis tools can interact with each other. Yeah. So some software has include this aspect. Yeah. So we can create the structure, we can create the layout, and then we can simulate the functionality of the device. For layout, we can use AutoCAD, CorelDRAW, Edit, etc. Yeah. Some extension of this project can also be used for fabrication, yeah, in some instrumentation, such as for e-beam lithography. So we can create the structure or the layout using AutoCAD, and then we convert the file, and then we bring the file into our e-beam lithography. From this machine, so the file can be used to directly create the structure. For model analysis, we can use COMSOL, IntelliSuite, CoventorWare, etc. File extensions such as GIF, CDR, GDS2, DXF, and many other AutoCAD file extensions can be used for the direct fabrication. So this is an example of simulation tools that we use in our laboratory. So we use COMSOL for finite element analysis. This section actually will be given in a special class, special lecture. Dr. Farhan will give this lecture. I show you a brief overview of this analysis software. COMSOL has 4 main modules, such as electromagnetics module, structural mechanics, and acoustic modules, fluid flow and heat transfer modules, and for chemical process module. In electromagnetic module, so there are many software can be used, such as for AC/DC, RF, wave optic, plasma, and semiconductor. So we can analyze this problem. And for structural, mechanical, and acoustic module, so there are many problems can be solved for structural mechanics, MEMS, especially for our project. We using this module. We usually use this module, and fluid flow, such as for mixer, microfluidics, and also for CFD, and another module is chemical engineering modules for electrodeposition or electrochemistry. Yeah, okay. This is a module in AC/DC that include the model for capacitors, inductors. So if you have project regarding capacitors, you can use AC/DC module. About motors, sensors also. Here we have also modules for model the dielectric, generators, about electromagnets, actuators, transformers, and also some electromachinery, for electrical machine problem. This is semiconductor module for semiconductor model. So we can here solve the problem about the Fermi-Dirac Maxwell statistic, band gap, and also for here we have for heterojunction, for compound semiconductor, and so on. So this module has the application area for design of bipolar transistor, MS diode, MOSFET, and so on, MOSFET device, and also for diode, Schottky diode, PN junction, and etc. And also for analysis of solar cell and LED or photodiode. While by MEMS, module for MEMS, there are some products features that can be used to analyze, such as piezoelectricity, solid mechanics, thermal stress, thermoelastic, vibrations also. So we can model this problem. The application of MEMS modules to analyze the accelerometers, actuators, surface acoustic wave to analyze the cantilever beams, capacitor, gyroscope, piezoelectric device, RF MEM, sensors, etc. Yeah, so it's very useful. Okay, then microfluidic module. So some project at IMEN has to do with the microfluidic. So there are many features can be used here, such as here capillary force, electrokinetic aspect, flow in porous media, laminar flow, which is the specific characteristic of the microfluidic, and then particle tracing method, yeah, for particle manipulation process. Okay, application areas are in capillary device, for dielectrophoresis, DNA analysis, electrokinetic or electroosmotic, yeah, lab on chip, magnetophoresis. So for microreactors, micropump, and micromixers, microfluidic sensors, and also for micromixer application. This is some model in chemistry or chemical process, such as module for process anodizing, for electroplating, electrodeposition for PCB, yeah, etc. Okay. Normally, after finishing the design of the system or the design of the process, so we can bring the result for evaluation. This is another important parameter in MEMS design, which aim to have the good accuracy of our design, of our theoretical analysis, to enable easy of iteration. Yeah, we call this as manipulation process. That means if there is something wrong in the result of our process, we should be able to repeat the process with good with improved result. Aim also to able to handle large system complexity, to handle multi-physics simulation, and also the coverage many aspect of physical effect. This is the concept how to evaluate, to verify, and to validate our simulation analysis. Mainly, our simulation apply to study a real system. So this can be conducted. The verification and the validation can be conducted by compare to an existing system. to compare with the existing analytical result. Yeah. Here we can see we can compare our simulation analysis with a published report or with a theoretical calculation, or we can also fabricate the design system or the design device by sending to the vendor, sending to the outside for fabrication. So we make the comparison, we measure the parameter, we can raise the limit, the deviation, and the tolerance, etc. So the result of this comparison can be used for suggest for optimization to improve the analysis. So that's why we call this process as the manipulation process. We can repeat, we can go back to our design, we change the parameter, we change the design, we change the layout, we change the geometry, and then we refabricate. Okay, this is the last section, case study for MEMS design. Here I would like to introduce a process fabrication of a design of microinductor coils that is used for RFIC and magnetic actuators. This is the workflow. For the design, MEMS design, we only capture this part. So there are the geometry profile and also the technology profile. For the device and process design, so we can use this in a parallel. So we can design the geometry of the inductor. This is a planar inductor that is wound side by side on a planar surface. And also we can design the structure of the inductor. So we can see here there are many layers of the device, such as the substrate, the insulating layer, the first metal, and then the next insulating layer, the second metal insulating layer, and the top metal layer. So this design or this analysis can be done by using COMSOL or IntelliSuite or Ascetic. Okay? After finish this work, so we can, for the geometry profile, we can create the mask. Okay? For the technology profile, yeah, by considering the geometry, so we can simulate and then we extract the model. Yeah? So we come to the evaluation, design evaluation. When finished, then we can fabricate and we characterize and we validate our analysis. So this is the geometrical consideration of the planar coil. So it consists of conductive metal trace formed in spiral structure. Eh? So this is the starting point of the coil where the current flow in, and then this is the end point where the current out. Yeah, so this should be go to the bottom layer of the metal and should be contacted through a via. So we call this as bridge. Yeah? So the geometrical parameter include the width of the trace, the space between the metal trace, the number of winding, the material used as the conductor material, such as copper, aluminum, gold, etc. This is the technological consideration. So we have many layers: substrate, insulating layer, bottom metal, insulating, and also the via to contact with the top metal layer above the insulating. This is the model, the theoretical calculation of the inductance. So if we consider here the inductor is designed with two coils with having mutual inductance between each coil. This is the primary coil and this is the secondary coil. This is the structure. We have the substrate, insulating layer. We have bottom metal. We have the via to connect with the top metal. So this can be modeled by using theoretical P-circuit model. This is the model of the planar inductor. So consists of the impedance of the coil, the parasitic impedance, due to the losses factor of the substrate and the insulating layer, and we can calculate the impedance of the inductance. So beside the using the theoretical calculation to analyze the inductor, so we can use also ascitic and COMSOL for simulation. The simulation of the device can be done using ascitic, COMSOL, or Coventor, while the layout design can be done using L-Edit, CorelDRAW, or AutoCAD. This analysis is done to understand the relationship of the geometry and the layer structure to the coupled inductor or transformer characteristic, such as the inductance, the resistance for various winding number, width, space, inner diameter, outer diameter, the thickness of the oxide layer, and to estimate the performance of the inductors, such as its quality factor or the coupling factor, etc. So this simulation also to provide the board to provide optimal design for the fabrication. So this is the result that we got from the simulation, such as if we increase the width, so the quality factor will also increase. However, the inductance will decrease. Resonant frequency decrease also. Coupling also decrease. However, if we increase the winding number, so quality factor is depend on other aspect. So however, the inductance will increase. Resonance decrease. Coupling factor also increase. So that means the width, the space, and the winding number strongly affect the resistance, the inductance, and the Q factor. And the coupling factor will be improved when space and width decrease, etc. Yeah, that means this is the trade-off between coupling, resonance frequency, coupling factor, and the size. If we want to have a high Q inductor, so maybe we should lower the spacing. Yeah. However, or we should decrease the oxide thickness. However, maybe the result for K will be reduced, etc. Yeah. So this trade-off should be considered for a certain device function. So therefore, we have to consider the availability of the material, the availability of equipment for the process, the availability of the test and measurement instrumentation for characterization, and the specification of the provided instrumentation in order to enable to validate our simulation, or in order to enable the to verify our analysis. Okay. Otherwise, we send our design to a vendor or to oversee. Okay, that's all my lecture for this section. Thank you very much. Okay, is there any question? Ada soalan? Ada ya?
Ada Pak.
Ada tanya, please. Ada ya? Okay, we rehat ya. Rehat agak terasa.
Pak, ada
Ya.
soalan tu.
Iya, oke.
Dekat chat.
Ada soalan tadi ya?
Daripada Anis Amirah Alim. Kata macam mana nak dapatkan license software tu?
Oh, sekejap. Kenapa saya tak dengar? Tadi soalannya?
Dekat meeting chat, dia punya chatting chat.
Oh,
dia tulis di situ.
Macam mana nak dapatkan license software? Okay, kita so we use console ya. We use console in iMan. Actually license software ni mungkin sudah beberapa lama expired ya. Saya ada kontak dengan kita punya apa namanya supplier. So biasanya dia bagi free, bukan free, dia bagi apa nama dia ya? Yalah, free license for a limited time. So dia bagi sebulan. Ya, dia bagi sebulan. Beberapa hari lepas dia tawarkan saya, nanti insyaallah bila PKP ini dah selesai, student boleh masuk makmal, kita boleh we can ask the ini ya, the license, ask our supplier to send the license for trial version, trial version, bukan trial version, they give us full version but limited for only 1 month. Ya, and then biasanya kita beli license. Setiap tahun kita beli license. Prof Azlan dia ada budget untuk beli. Nanti kita bincanglah untuk kita proceed. Oke? License software ini hanya diinstal di satu komputer saja, di Makmal MEMS. Ya, nanti boleh tanya saya atau tanya Dr. Ronira yang mana satu. Itu ada dekat sana. Trial version pun boleh guna. Jadi semalam saya ada kontak dengan supplier, dia tanya juga setakat ini macam mana pakai. Saya bilang aja saya pakai trial version. Meskipun trial version ini tak komplit ya, tapi untuk student saya rasa boleh pakai. Seterusnya kita perlu berhati-hati juga kepada pelajar, to the student. Please be careful to publish your paper, as we don't have license ya. We don't have license since many months, yes, many months ago. So if you want to publish the paper, please don't mention about COMSOL. Better you mention only finite element analysis. Yeah, because some module in trial version is not included. Yeah, so apabila kita publish, so orang COMSOL dia tengok, ini tak ada dekat inilah yang kamu beli, lesson yang kamu beli, lesson yang for trial version, kenapa boleh ini? Nanti jadi masalah pula, nanti dia banyak tanya. Meskipun terkadang kita buat simulation, masa dia bagi free license for limited time. So better mention only finite element analysis. Okay. Any other question? Tak ada ya? Okay, saya rasa itu saja the first section of our lecture. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh. We come again in 15 minutes ya.